Okay, in this lesson, 2.7.8, we're going to be going backwards a little bit. We're going to look at the solutions of a system of linear inequalities, and we're going to try to understand those, be able to identify those. So our objectives are to determine if ordered pairs are solutions to a system of linear inequalities, and then we're going to also understand how the solution set differs from a system of equations. So let's go ahead and talk about what the solution set means and how it differs from a regular of linear equations. The solution area in a system of inequalities is that part of the plane in which all the points are solutions for all equations in the system. And you've just finished graphing systems of inequalities and shading the solution areas for both. And you were able to see that where they overlap, those points would be solutions to both equations. And we tested a point in the overlapping area in order to make sure that was true. This differs from a system of linear equations in that in a system of linear equations, the solution is only one point. It's where the lines intersect. Let's look at some examples graphically. So here we have a system of linear inequalities, both graphed. You can see the one on the left has the blue area shaded, and the one on the right has the purple area shaded. And what we want to determine is which one of any or multiple points are solutions to these linear inequalities. And remember that one way we can do that is we can take each of these points, plug it into each of these equations, and see if it's true for both. But if we have a graph, it's a lot easier to determine. So if I take this point, -1, 2, let's find it on the graph. So if I go over here to -1, 2, that's right here. And that point is in our common shaded area. This shaded area is a solution to both of these equations. So this point is in fact, yes, that is a solution to both, to the entire system. Let's take the point 1, 3. 1, 3 is up here. That is also a solution to this system. That is in the more of a darker purple shaded area. So that point works for both. It is a solution for both. Now let's look at the point -1, -1. That would be down here. That point is neither a solution to this equation or this equation. It's not in any shaded area. And if you were to take this point and plug it in, -1 is greater than, and -1 plus 1 is 0. Well, -1 is not greater than 0. And if we look over here, -1 is greater than a -1, which turns it into a +1. Well, -1 is not greater than +1, so you can tell by testing that it doesn't work either. So this one is no. All right, let's look at a couple more graphically. So here again we have two systems. And notice we also need to pay attention to the lines. These are both solid lines, and notice that our equations are greater than or equal to on both. They have the or equal to on both. Okay, so let's go ahead and plot our first point, 1, -1. So we go over here to 1, and then we go down here to -1. And if you'll notice, this point is not a solution to either of these because it's not in any of the shaded regions. Now let's look at 2, 3. So here's 2, 1, 2, 3. And this point is in our commonly shaded area. So this point is a solution to both of these equations, meaning that if we were to plug it into this equation, it would work. And if we plugged it into this equation, it would also work. Now let's look at this last point here, 1/2, 1/2. So 1/2 is right here in the middle, between 0 and 1, and then up about halfway, so it's right here at the intersection. In this situation, this point is a solution to both of these equations. And the reason is because this line is solid and this line is solid. And if you remember, if you have a solid line, that means that the points on the line are also solutions in this inequality. And since both of these lines are solid, this point is therefore a solution to both. Now, if one of these lines was dashed, then the point would only be a solution on the solid line, not the dashed line. But as it stands, this point is a yes. Okay, let's look at another one. So let's go ahead and find this point, -1, 0. So -1, 0 is here, and that falls into our commonly shaded area, which is this green color. So this is a yes, meaning that this point, if we plugged it into this equation or this equation, we would get true statements. Now let's look at 0, -2. That's down here. That point is a solution to this equation right here, the 5x minus y is less than 9, but it is not a solution to this equation up here. Notice that this equation solutions are all up above. Okay, they're all up above up here, and that point is not part of that. So this point is no. Since it is only a solution to one of the equations, it does not work. It has to be a solution to both. Now let's look at 1, 3. So 1, 3 is up here. It's also in our common shaded area, so that point would be a solution for both. So that is a yes. All right, let's look at one more graphically. In this situation, we actually have more than 2 equations. And remember that a system just means more than one. So we can have 3 or 4 or even 5 inequalities or equations if we want to. And we do have 3. We have this purple one, we have this brownish one, and we have this kind of red colored line. And you can see where they're all shaded. And the key is to find the overlapping area. Well, the red one is shaded this way, down below, less than. This brown one is shaded up, greater than. And it looks like this blue one is shaded down, which is a less than. So our common area is in this triangle where you see all 3 equations written. That is the overlapping area. So let's look at our points. 4, 1. So that point is right here, and that is a solution to our blue equation right here because it's in the blue area, but it's not in the overlapping equation. So this would only be a solution to, well, actually it would be a solution to our blue area, and then actually our green area is shaded out this way, so it would work in both of the green equation, or brown I should say, brown equation, and the blue equation, but not in all 3. So this is no. Let's now look at 0, 0. So that is right here, and that is in our overlapping area. So if I tried it in all 3 of these equations, it would in fact work. So that one is a solution to all 3, which means it's a solution to the system. Now let's look at -2, -5. So -2, 1, 2, 3, 4, 5 is down here. So it looks like it is a solution to our blue one. It is also going to be a solution to our red one because our red one shades down this way, but it is not a solution here to this brown green one, whichever color that is. So this one is no. In order for it to be a solution to the system, it has to work for all 3 of our equations. Okay, let's now go to verifying this algebraically. So you may be given some systems and then some points to determine if in fact these are solutions, if they work in the system. So the way we go about it is we would just try each one in the system, just like our test points when we graph, to see if in fact they work. So in the first equation, we'll plug in a 7 for our y, we'll plug in a 3 for the x, and we'll test to see if it's less than or equal to 0. 7 times 2 is 14, and this was a 4. 4 times 3 is 12. Is that going to be less than or equal to 0? And 2 is not less than or equal to 0. So this is no. Okay, so now let's try B. So we don't even need to try A in the second one because it didn't work in the first one. So let's try B in the first one. So we have 2. We're going to go ahead and plug in a -1. That's our y. Minus 4. Plug in the 2 for x and see if it's less than or equal to 0. 2 times -1 is -2. And then -4 times 2 is -8. And is this going to be less than or equal to 0? And yes, it is. So b worked in our first equation. Now we need to try it in the second equation. So we would have 3 times negative 1 is greater than 2 minus 6. 3 times negative 1 is negative 3, and 2 minus 6 is negative 4. Negative 3 is in fact greater than negative 4. So we have tested this point and found that yes, in fact, it is a solution to our system. It works in both. Let's try our last point. Let's try point C. So if we plug in, we have negative 6 comma 0. We have 2 times 0 then, minus 4 times negative 6 is less than or equal to 0. Well, 2 times 0 is 0. Negative 4 times negative 6 is positive 24, and that is not going to be less than or equal to 0. So we know right away this is no, and we don't even need to test it in our second equation. Okay, in our next example now, here's a situation, this is our final example, where we actually do have 3 equations. We need to make sure that the points work in all 3. So let's go ahead and test our A point first. So here we have 4 is our y, is less than or equal to 3/2 times 4 minus 1. So simplifying that, 3 times 4 is 12, and 12 divided by 2 is 6. So 4 has to be less than or equal to 5, and it is. So now we can test it in our second equation. And this is just y is greater than negative 4. Well, y is 4. Is 4 greater than negative 4? It is. So let's test it in our third equation. We have negative 2, plug in the x value of 4, plus a y value of 4 as well. Negative 2 times 4 is negative 8, plus 4 has to be less than or equal to 3. So negative 8 plus 4 is negative 4, and that needs to be less than or equal to 3, and it is. So this point satisfies all 3. It is, in fact, a solution to our system. So we would just want to continue on and test the other ones, and probably the easiest one to test it into is the second equation, because you only have to test one number. So let's go ahead and do that just to speed up the process. So we'll go ahead and test the middle equation. So negative 9, that's our y, is that going to be greater than negative 4? It is not. So our b is out. That's a no. Now we can go ahead and test the final one, which is c. And let's do the middle one. So we have a negative 5 here for y. Is that greater than negative 4? And it is not, so right away we know that that's a no. And that is how we can quickly test by putting it into the easiest equation versus starting with a more complicated one. And that is one way to test for solutions. So hopefully at the end of this lesson now, if we go back to the start, we have met our objectives. You are able to determine if ordered pairs are solutions, both graphically and algebraically, and you can understand how the solution set will differ from a system of